Hi class, we're on to week 7 of our experiments, the oxidation and reduction reaction experiment. Again, please keep in mind to review your textbook. You'll have to read chapter 10 in order to successfully understand this lab. Alright, so let's go on to our pre-lab lecture. Again, this corresponds with chapter 10 from your textbook, so please make sure you read it, review it before we get to lab. We'll cover this content next week in class. So we have a few goals for experiment 7. First is to understand the meaning of oxidation and reduction, to rank several metals in a series from most active to least reactive. We'll go over what we mean by that. To place hydrogen in the activity series. Again, we'll describe what activity series is. And lastly, to relate the concept of oxidation reduction, which we normally call a redox reaction, to a real biochemical process. That's part C of this week's experiment. All right, so let's just dive into the course content that we need to really successfully understand what we're doing in lab this week. All right, so we said we have oxidation reduction reactions. We usually call these redox reactions. What are redox reactions? They are reactions where electrons are transferred from one reactant to another. For that reason, oftentimes redox reactions will be referred to as electron transfer reactions. So how do we identify if a reaction is redox or non-redox? So one thing to note, it's really important that not every reaction is a redox reaction. Some reactions are redox, some don't have an electron transfer. So we have to be able to identify which ones are redox, which ones are not redox. So the way we do this is by identifying the oxidation state or oxidation number. We use those two terms interchangeably, and I've mentioned them a few times over the course of the semester already. So how do we do that? Well, we need to keep track of our electrons. And we have two cases here. We have electrons that are gained and electrons that are lost. So we have to keep track of electrons gained by the substance being reduced and electrons lost by the substance being oxidized. So notice the terminology that I'm using, reduced and oxidized. Okay, so let me just highlight a few key terms here. So I have electrons gained, and when I gain electrons, that means my substance was reduced. So let's highlight those the same color. And if I have electrons lost, that means that substance was oxidized. Okay. So now the question is, well, how do I actually figure that out? So your textbook has a really great step-by-step instructions, or I should really say they're more like rules in assigning oxidation states. You should bring, as always, bring your pre-lab lecture notes with you to lab because it's going to help you figure out what you're doing, and it'll relate what we're doing in lecture with lab. So we have 7 rules that you'll need to memorize. Not before lab, but certainly for lecture. So rule number 1 simply states that the oxidation of an atom is the most abundant naturally occurring form of an element is typically 0. So an example of that, if I simply just have copper, that means its oxidation state is 0. Okay? The oxidation state of oxygen atom in a compound is almost always -2. Almost always, because I've said before, we always have exceptions in chemistry. The oxidation state of a hydrogen atom in a compound is almost always +1. So these are kind of easy ways to tell you if you have, for example, copper oxide. The oxidation state of oxygen is -2. We have to figure out what the oxidation state for copper is. Rule number 4, the oxidation state of any group 1 atom is always +1. We kind of already know that, right, from the alkali metals. Oxidation state of any group 2 atom is always +2 if it's in a compound, right? So here we're talking about atoms in a compound. Rule number 6, the oxidation state of a monatomic ion equals the ion's charge. What's a monatomic ion? An example of this, let's stick with copper. If we have copper 2+, the oxidation state of copper 2+ is simply 2+. All right, the halide rule. A halogen atom in a compound usually has an oxidation state of -1, except when it's bonded to a more electronegative atom. Pay attention to the exceptions because you will be held accountable to know these exceptions. But in general, they're -1 unless it's bonded to a more electronegative atom. An example of that, if you have chlorine bonded to fluorine, fluorine is the most electronegative atom in the periodic table, so therefore that oxidation number is going to change. Rule number 7, the sum of the oxidation states of atoms in a chemical formula must add up to the overall charge of a molecule or ion represented by the formula. So this is all, to you, you might say, well, I already know this because I've done this at some point. And you're absolutely right. We have done ways to figure out oxidation states when we have to write chemical formulas. But let's just go over some examples. So an example here, I have MgBr2. Let me apply my rules. Br is a halide, so therefore I'm applying the halide rule. And by applying the halide rule, I know my oxidation state or oxidation number for Br is -1. Magnesium, I check my periodic table, I see that it's in group 2, so therefore rule number 5 tells me that magnesium is +2. Okay? Let me double check. So rule number 7 says, well, if I add up all of the oxidation states, it should equal to the charge on the formula. And here I don't have a charge, so I have +2 for magnesium times 2, because I have 2 moles of bromine atoms in this compound, times -1 is the charge on bromine, and I simply get 0. So this is a nice double check that you can do on your own. Let's do a non-neutral compound. So we have a polyatomic ion carbonate. This is one of the ones you have to memorize. All right, so do we have a rule about oxygen? We do. Rule number 2. Rule number 2 says my oxygen's always -2. I don't have a rule for carbon. So if you notice, we only have 7 or 8 rules here. There are many more atoms in the periodic table, so most of the atoms in the periodic table don't have rules. How do I calculate the oxidation state for carbon? And this is essential because if you can't calculate your oxidation state, you won't know if it gained or lost electrons, okay? So let's do a little chart here. Let's list our atoms and let's list our oxidation state. So we have 1 carbon atom. I'm going to list all 3 oxygens individually. Carbon, I don't know what it is, so I'm going to simply state X. Each oxygen is -2 for a total of -6. If I add these up, I have to figure out carbon first before I add them up. So let me actually tally the math out here. So I have X minus 6 is equal to, my charge should be -2. So therefore, if I solve for X, it's equal to +4. So now if I sum these up, I have +4 plus -6 is equal to -2. So my last rule, number 7, this works out because I have -2 here and -2 here. And my oxidation state for carbon is +4. My oxidation state for oxygen is -2. Careful, it's not -6, it's -2. Okay? So let's state some general rules. If the oxidation, and I'm just going to abbreviate oxidation as ox, state of any atom changes during a chemical reaction, that means a transfer of electrons must have occurred. And because there's a transfer of electrons, therefore this is a redox reaction, okay? So if your oxidation state changes throughout a chemical reaction, you have a redox reaction. All right, let's define what oxidation and reduction are. So oxidation is when an atom, not a compound, an atom loses electrons. That's what we say That's what we call something being oxidized, if it lost electrons. Remember, one way to pick this up, we know electrons are negatively charged species. Therefore, if it loses electrons, it's going to increase in positivity, right? So that means when it loses electrons, the oxidation state will now be higher. And I'll give you an example shortly. All right, what about reduction? Reduction is when an atom gains electrons, and that's what we call something being reduced. Okay, we know electrons are negatively charged species, so therefore what's going to happen to the oxidation state? Well, the oxidation state is now lower because it gained negativity, so it's going to decrease. All right. Pause this video at any point if you need to think about these concepts some more before we move on to examples. Let's have an example here. We have CH4, which is methane, plus, and I'll just balance this equation, plus 2O2 gives me CO2 plus H2O. As a reminder, what kind of a reaction is this? This is a combustion reaction. So redox reactions, I want to point this out, is not a separate type of reaction. Redox reactions can occur in combustion, decomposition, double replacement. They could occur in any type of reaction. It's just an additional thing that we need to keep in mind. All right, so let's use a different colored pen here. We have methane gas plus oxygen gas breaks down into CO2 and water. So let's identify the oxidation state. So we have a rule for hydrogen. The rule says it's almost always +1. So I'm just going to say it's +1. Okay? That means I have to use this method here to calculate carbon. So I have 4 times 1 is +4. It's a neutral compound, so carbon must be -4. If you're confused here, stop the video, do the tally for carbon using the same exact method, and see if you get a -4. All right, we have a rule for the oxidation state of an atom is the most abundant naturally occurring form of an element is typically 0. This is an element. This goes back to the first lecture of this class. That means its oxidation state is 0. So step number 1 in a chemical reaction, if you're trying to figure out if it's a redox reaction, you identify the oxidation state of every element you have in your reaction. All right, rule number 2 tells me oxygen is -2. I go through my tally method here to calculate carbon. Carbon is now +4. Okay, oxygen here is -2. We know rule number 3 tells me hydrogen is +1. So now I match up the elements from one side to another. Hydrogen did not change, so I'm not going to match those up. And I see that oxygen's located in 2 places, and it did in fact change. So if I pay attention to carbon, it went from -4 to +4. It went from a negative number to a more positive number. Therefore, carbon lost electrons, it lost negativity, and this is what we say has been oxidized. So what was oxidized in this reaction? Carbon was oxidized in this reaction. Similarly, oxygen goes from 0 to -2. It gained negativity, it gained electrons. And if it gained electrons, it means it was reduced. So what was reduced in this reaction? Oxygen was reduced in this reaction. Okay? Now, if we have a component that was oxidized and a component that was reduced, that means we have to have agents that result in these oxidation reductions. All right, so we have oxidizing agents and reducing agents. So let's define these first. Oxidizing agent is a reactant that causes oxidation, which remember again is a loss of electrons of another reactant. And how does it do this? It does this by accepting electrons from it. Okay, a reducing agent is a reactant that causes reduction, which we know means gain of electrons. So this reactant, a reducing reagent, causes reduction of another reactant. Okay. let's go back to the example that we were just working with. So we have methane gas plus oxygen gas combust to give us water and CO2. So we had said before that that carbon was oxidized and oxygen was reduced. So according to these definitions, methane, so a reducing agent, is now the full reactant, not the atom. Okay, pay attention to that because students always confuse that. The reducing agent is the agent in which an atom was oxidized. So therefore, in this case, my reducing agent is methane, CH4, and my oxidizing agent is the agent in which an atom was reduced. In this case, that was elemental O2, so I have that being my oxidizing agent. A nice rule of thumb, and you might want to write this in a different color, is that the substance that was oxidized is actually your reducing agent. And pause the video for a second, think about if it doesn't make sense based on this definition. And the substance that was reduced, that is now my oxidizing agent. Remember, because it took electrons from something else. All right, so that's a nice rule of thumb. So basically, once you figure out what was oxidized, what was reduced, what was oxidized is your reducing agent, what was reduced is your oxidizing agent. Okay, great. So now let's move on to an example that's very similar to what you're going to be doing in lab. All right, so in lab, part A and part of part B, actually, you're going to put a piece of metal into an aqueous solution. All of your solutions are some form of a nitrate. So for example, in this case, this is a copper nitrate solution. It's an aqueous solution. Remember in chapter 8, we said an aqueous solution basically means in a beaker, you have floating ions of copper plus and floating ions of nitrate 3 minus, nitrate NO3 minus, okay? So we don't have a single compound. We have to remember they dissociate in solution to form these ions. So here we have a zinc strip. It's in a solution of copper nitrate. All we really care about is the copper. Nitrate is inert in this case. So here in this reaction, I want us to assign the oxidation states of the atoms and ions in the reaction below. So let's write a reaction for this. We have zinc, metallic zinc. So let me rewrite this. Okay, it's a metal, plus copper ions, and we know that's aqueous. These undergo a redox reaction, and I know it undergoes a redox reaction because my zinc goes from a beautiful shiny metal to, and you might want to zoom in on this now, notice how it's kind of this rusty color. So what's happening here is your copper is actually plating your zinc. It's depositing on your zinc. So now we're actually forming solid copper, and this is a method that's called electroplating. It's a method that's actually still used in industry. This is how gold is plated onto some materials. You have a sheet of gold over jewelry. It's all redox chemistry. So it forms copper solid, and now you have zinc ions in solution. And I'll show you a schematic in a moment on the next page. So is this a redox reaction? I can't answer that question until I've assigned my oxidation states. So zinc, according to rule number 1, is 0. Copper, according to rule number 6, is +2. Copper 2 plus. Copper solid is 0 according to rule number 1, and according to rule number 6, zinc is 2 plus. So now let's match our elements from one side to another side, and I can see that my zinc increased in oxidation state, so therefore it was oxidized. And I can see my copper 2 plus, my copper ions, decreased in oxidation state, so therefore it was reduced. So to answer the first question, is this a redox reaction? Yes, it is. And how so? Because my oxidation numbers, oxidation states of zinc and copper did in fact change. One thing to note, if my oxidation state of zinc changed, that means the oxidation state of copper has to have inherently changed. What was oxidized? Well, we just went through that. It was zinc that was oxidized. What was reduced? It was copper that was reduced. So now, what is my oxidizing agent? Well, remember I said up here, let's just use a shortcut. An oxidizing agent is what was reduced. So in this case, what was reduced is my copper 2 plus. All right. What is my reducing agent? My reducing agent is the thing that was oxidized. So therefore, in this case, it's my solid zinc. I should note that your oxidizing and reducing agents are always on the reactants side. So maybe write a note here that it's always on the reactants side. Okay? Pause the video right now, go over this problem again, and see if it makes sense to you. Okay? So, now I have a question for you. How do I know which ways electrons flow? So in the previous example, we had a zinc strip, a solid piece of zinc in a copper nitrate solution. And what happened here, this is a really nice diagram because here I have metallic zinc, I have copper ions. The zinc metal is giving up electrons. It's being oxidized to copper ions, which is reducing the copper ions to form copper atoms. So this is a reduction that's happening here, and that's why you have what we call copper plating on zinc. Okay. But what happens in a case if you have copper strip in a zinc nitrate solution? Well, copper's not going to give up electrons to zinc ions. And why is that the case? Why is it that in one case zinc was giving up electrons, but here nothing's going to happen? If you can keep this for days, for weeks, nothing will happen here. Why is that the case? Let me just remind you and write a chemical reaction here. Here we have zinc metal plus copper ions aqueous. And by the way, for part A of your experiment, you're required to write these reactions, so make sure you understand how we write these. So that's the reaction that's happening here. Again, nothing's going to happen in this case here, so if I were to write a reaction, that's what I have in my beaker. This is not going to proceed forward at all. Why, again, is that the case? Well, simply some metals lose electrons more readily than others. And we call these active metals. And what we mean by that is that they're simply oxidized more easily. Remember, if you lose electrons, you become oxidized more easily. So that's really the answer, but you're probably still not convinced. Okay, so here we have zinc metal. It's going to lose electrons. So if zinc metal is in a copper ion solution, your zinc metal is going to lose electrons to give them to the copper to deposit copper metal. So electrons will always flow from the more active metal to the least active metal, and not vice versa. So the question that you might ask right now, well, how do I know which one's more active than the other? Well, first of all, that's what you're doing in part A, but there's been a series of experiments conducted exactly what you're going to be doing to tell us which metals are more active than the others. And that is called an electromotive series. It's also referred to as the activity series. And what is the activity series? What's the electromotive force series? It simply allows us to predict the more active metals in which redox reaction will be spontaneous, and thus the direction the electrons will flow. So this is your EMF series. You don't have to memorize this. I will always give this to you on an exam. You're going to have your pre-lab lecture notes with you in lab. So what I want you to do after you've conducted your experiments and you've ranked your most active to least active metals, I want you to compare it to what theory tells us, okay? All right, so How do I use the EMF series? To simply tell me if a reaction is going to be spontaneous. And what do I mean by spontaneous? If it's going to occur. Okay, so in one example, I have zinc ions, an aluminum strip, an aluminum metal in a solution of zinc ions. That will form zinc metal to aluminum ions. So the question is this going to be a spontaneous reaction or not? How do I identify this? Well, on the electromotive series, I need to identify, so if this was on paper, identify where zinc is, identify where aluminum is. Zinc is a less active metal than aluminum, or I should say aluminum is more active than zinc, so therefore aluminum will more than happily give zinc its electrons. So if we notice here, zinc gained electrons. It went from +2 to 0. And where did it gain these electrons from? It gains the electrons from aluminum, and this is in fact a spontaneous reaction. So if it gained electrons from aluminum, aluminum was oxidized. And why was it spontaneous? Because aluminum is higher on the electromotive force series, the activity series, than zinc, so therefore it will more than happily give zinc its electrons. So this reaction is spontaneous. Now let's say if I have it the other way around. What if I have solid zinc in an aluminum solution? Will I get this formation? No, because zinc is less active than aluminum metal, therefore it's not going to want to give its electrons to aluminum, so this reaction will not proceed. Okay? Also, I want to note, this is sometimes what we call a half-cell reaction. Okay, because again, you're going to be required to write these reactions in part A. Another way of writing half-cell reactions, and this is the more appropriate way, is simply showing your metal, your ion forming your metal. Okay, so I have zinc 2 plus aqueous. If I add 2 electrons to it, and these electrons are coming from aluminum, I get zinc metal. We'll go over that in class. All right, so that's really the background on this week's experiment. It's all identifying your redox reactions, which ones oxidize, which ones reduce, and ranking your metals from most active to least active. So in part A of your lab, you're actually going to come up with your own activity series based on observations that you see. I suggest that you expand this table or have a table on your own and record the initial observations of all metals and solutions that you're using, okay? So in the experiment manual, we tell you that simply indicate the reactivity using the following nomenclature. So you can use plus for slightly active, plus plus for more active, plus 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 for extremely active, etc. But I want you to also describe what you see. So please pay attention, because you'll get points taken off if you don't do that. So record observations, okay? Recording observations is more than just plus and plus plus. All right, so for part A, I suggest that you set up all of part A entirely. You're going to wait 5 to 15 minutes before you make observations. You should make initial observations as soon as you put the metal in your nitrate solutions, in your aqueous solutions. Make observations, then come back 5 to 15 minutes later, record observations again. So start all of these at the same time, and then while you're waiting, and if there's time, maybe you should go on and move on to part B and set it up. Okay? But if there's no time, and I don't want you to rush this, you have plenty of time in lab, I want you to record absolute initial observations, and then observations as soon as you drop the metal in the nitrate aqueous solutions of the other metals. You're not going to do magnesium and magnesium, for example, so this is X'd out, and it kind of makes sense. You're not going to get anything if you put a metal in its aqueous solution. You set up all of these, you write the immediate observations, you come back 5 to 15 minutes later, you write observations again, and those are your absolute final observations. So from part A, after you've completed part A, I want you to rank the metals in order of decreasing activity. So you're basically going to write your own activity series based on your observation. I don't want theory. You're going to be graded on whether or not your ranking is appropriate to your observations. An example of this, let's just say that magnesium, I noticed it reacting much more strongly than aluminum. So how do I rank this? If it reacts much more strongly than aluminum, that means that means magnesium is higher on my activity series, or the electromotive force series, than aluminum is. So if I were to rank it, I'd put magnesium, then aluminum, and then etc. So that's what we mean by ranking for part A. Okay? Now part B, so if you notice in the electromotive force series, the activity series, I actually have hydrogen here. So in part E, you're going to be placing hydrogen in the activity series. You're going to be using the 6 same metals again, but now you're going to put these metals in an aqueous solution of hydrochloric acid. And the goal from here, from part B, is you're going to place your hydrogen in the activity series based on how it reacts with the metals. Okay, an example of that, so let's say, let me take magnesium again. So let's say I put magnesium metal in hydrochloric acid, and this reaction, it's an instant vigorous reaction. And I would go further and describe what do I mean by instant vigorous reaction. And let's say I have copper and I add it to hydrochloric acid. I don't see anything at all, no reaction. And I would describe, no, my copper looks exactly the same. It's that same copper-like substance. No bubbles formed, nothing, no heat, no reaction. So how would I place hydrogen between these two? Well, I know I got a reaction from magnesium when I put it in HCl, so that means magnesium is more active than hydrogen. But I got a no reaction here, so therefore hydrogen is probably placed between copper and magnesium. Okay, so I want you to do that for all 6 metals and place hydrogen within those 6 metals. You can then, after you're done, check your activity series. Part C is a nice experiment because it's actually an example of biochemistry or biological chemistry in redox reaction. What we're doing in part C is we're going to have a decomposition of hydrogen peroxide, which is H2O2, and through that decomposition we're going to produce water and oxygen gas. And you'll actually see this happening. You'll see water forming, and you'll definitely see oxygen gas forming. From this, you're going to be asked to write a full balanced chemical equation of the decomposition. So notice we're using some of the nomenclature from prior lectures, decomposition of your H2O2, and from that, our new material here is you're going to identify what was oxidized and what was reduced. Okay? All right, so pace yourself very well, because this experiment can take a long time if you don't set it up properly and wisely. A few experimental logistics. Your post-lab for experiment 6 is due at the start of lab. No late assignments. You are working in pairs for this experiment. Follow the instructions carefully, and please come to lab having an action plan ready so you can hit the ground running. There is no post-lab quiz this week. Instead, there's a post-lab assignment that is due at the start of the following week's lab. As always, if you have any questions, ask me or any one of your lab instructors. Good luck in lab, and I hope you have fun.